Welcome back to the lecture on electricity price forecasting. This is the second day. Today we'll be covering the following topics. I'll start from some relatively simple techniques that can improve your forecasts. Then go on to a bit more advanced models, lasso estimated or generally shrinkage methods plus deep neural nets. Then talk again about probabilistic forecasts, but using some more advanced techniques. And finally, about financial evaluation of forecasting errors. So let me start. Well, first of all, we haven't really talked about it, but sometimes you need to, you can transform the variables. This usually helps. And the most classical transformation in economics is the logarithmic transform. And as long as your data is well above zero and only positive, then of course this is okay, and you can do such transformations. And the log has nice interpretation, so you can interpret as elasticity in the coefficients. So this is generally a good idea. So if you have very spiky data, the spikes get damped, whereas the low values get stretched down. So that's why you cannot have values close to zero, because they will become really strong, really big, highly negative values. So one option would be to add a constant to your data so that it is well above zero, then take the log. Okay, pretty naive. Or you can use a different transformation. And if you go to this paper here, with Bartosz, my former PhD student, and Florentil from Essen, we test 8 different transformations. So if you have original data series, and this is the original data series in the first panel here, and you plot the marginal distribution, so kind of take every point here and project it on one axis, and then here you have the distribution. Then this is what you get. It's essentially very heavy-tailed distribution, which may impact your estimates, especially if you are using squared errors to estimate your model. So an option would be to somehow make it a more symmetric, make it less heavy. One of the options is in this plot here. It's the what do you call it? Area hyperbolic sign, which from this distribution makes something like this one, which is much more concentrated, much more symmetric than the original one. Or you can do it, even go all the way and use the PIT, the probability integral transform, to make it any distribution you want. And I'll show in the next slides how you can do it. So in general, there's a whole zoo of these such transformations, which are often called variance stabilizing transformations. So they kind of compress the distribution and make it more regular, which is better for most methods that you use to estimate and fit to your data. So area hyperbolic sign is this function here. We use it quite often because it's relatively simple and can be used in many contexts. And in most cases, it improves actually the fit. So the transformation is this one here, just this one, and the inverse is just the hyperbolic sign. So that's also well defined. Also in almost any software we can find this function, so it's easy to apply. The area hyperbolic sign is the red curve here. So this guy here is the red one, and it's also here. So all of these transformations will be kind of smoothing out the very high value, so they kind of go down here and pull up the lower end of the distribution. That's the idea of how they work. You can, for instance, consider a transformation which is kind of like gluing together two logarithmic transformations. We called it a mirror log. It just has slightly different properties. And here's the function, a bit more complex. There's an extra parameter, because here in the area hyperbolic sign, there's no parameter to fit. It's just as it is. With the mirror log, there's a parameter. In this paper, we suggest just to use one value, but of course you can, in theory, you could try different and see which one works for you best. There's also, if you go to this paper by Michał Narajewski and Florentil, they suggested kind of a more accurate back transformation more computationally involving, and the differences are not huge. So still, I would go just with the simple ones that we have here. Now the PIT, it's something which is well known in statistics. It's defined as the empirical distribution function applied to your data. So if your input data, if x's are F distributed, then by the definition, they will be the PIT. So after you take these x's, the x's are F distributed, you apply the distribution function on them, what you get here is a uniform distribution 0, 1. Okay? Once you have a uniform distribution, you can do anything you want with it, meaning you take the inverse of, let's say, of a Gaussian, and you get a Gaussian, standard Gaussian distribution. So this is one thing you can do. But just looking at this part, so just looking at the uniform part, the PIT is a graphical method to assess the goodness of fit of a probabilistic forecast. Because here you have in the plots here in this column, you have 3 different forecasts of 3 different models. Doesn't really matter what the data is. I mean, selected prices, but doesn't matter what the models are. On the first one, you see kind of like a inverse cup shape. And the second one, you see a cup shape. And this one is more or less flat. So which one is uniform? No, of course, this one is uniform. So this is the best one out of these 3. This one has 2 heavy tails. This one has 2 light tails, and the other one has 2 heavy tails. So this is an easy way to see if your probabilistic forecast is relatively okay. But as I said, if you take the PIT, which is uniform U01, and apply the inverse distribution function of some distribution, for instance, the normal, so this is NP, we call it, or in this case, we take the inverse of the student T with certain number of degrees of freedom, for instance, in this paper with 8 degrees of freedom, then what you get, what you get here, this Y here, is N01 distributed. This one is T student distributed with some parameters. So then you can, so you convert such a distribution, essentially a distribution, into something like this. This is the Gaussian, this is the normal distribution. If you want student T, it would be slightly more heavy-tailed here. So these are also possible distributions. And in this article, the first one I'm mentioning here, also sorry, the second one here, you see a comparison over, I think, 8 different data sets, and you see a range of it. How do these transformations perform for markets for data from different electricity markets? The NPIT was actually used a bit earlier. There's a paper by Diaz and Planas. They called it differently. So kind of coming back to the discussion we had yesterday, sometimes the same methods have different names in different articles, different publications. So be careful what you are reading. Try to understand what exactly the authors had in mind. But then in other publication, native is something more than just a transformation. So sometimes the names can be a bit misleading. Now, the transformations, we can apply them to the prices. We can also apply them to the exogenous variables if they are also heavy-tailed. So this is kind of a universal tool. When we apply them, we should first normalize the prices. So the normalization is we take the price like here, subtract the mean in one version or the median in the second version, and divide. So if we subtract the median, we divide by the median absolute deviation. If we take the mean, then we divide by standard deviation. So this is kind of a standardization procedure, or Z-score. Again, different names used for the same procedure. The inverse, so this one here is just this function here. So we normalize data, apply the transformation, make the prediction on the transformed prices, take the inverse transformation, denormalize, and you get the predictions. Okay? This is the simple procedure. And this procedure really helps and almost always helps. Now, with the MAD, a lot of software has this implemented, but again, a word of caution, because different software has different standards how the method is implemented. And the difference is that there's a rescaling factor of 1.426 roughly, which is a quantile of the normal distribution. And for instance, in Julia and R, this multiplier is used by default. So what you get is already multiplied by this number. Whereas in MATLAB and Python, for instance, this is not the default case. So this multiplier is for making this kind of normalization by the median and MAD similar to standardization by the mean and the standard deviation. So different software can have this very simple method implemented differently. Okay, next topic, dummy variables. So seasonal decomposition. Introducing the autoregressive model, the expert model, I told you that there's a component which often are the dummies for the days of the week. And this is just an example. I write them out here explicitly. And again, let me repeat that if you have an intercept in your model, then you do not use the Sunday dummy. If you don't, you can use it. So you cannot have more dummies than the categories. Quite often you can use dummies for special events, like some holidays. I mean, World Cup matches, strikes, like the Munich strike, if you know it's coming in advance. The different possibilities to use them. If your period you're looking at is much longer, like a year, dummies for every day of the week, every day of the year, so 365 dummies is not a good idea. So you want something more parsimonious. And one of the possibilities is used to the Fourier decomposition. So essentially, a sum of sines and cosines to approximate your long-term seasonality. So this is an option. The thing is that if you use this to fit your annual seasonality, if it is actually repeating more or less in the next year, then it's okay. If it's not, then probably this is not a great idea. So that's what you can use. You could also use this Fourier decomposition for the weekly seasonality, but then you would need at least 3 terms, but usually more, to get more or less what is happening during the week, where you have the Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday are much lower. So to catch this kind of weekly pattern, you would need more than 3 even components. A different behavior. I mean, if you think about cyclic behavior, okay, in statistics, there's a difference between a seasonal component, a seasonal pattern, or a cycle. A cycle is something irregular. Seasonal is of a fixed period. So you have something which is seasonal of a fixed period. This is cycle, but let's say business cycles are something which, so you have the economy goes up and it goes down, but the number of years it takes to go up and down is not fixed. And here we can also have such a situation that in the longer term, in our price series, we can have rather cycling behavior than exactly a fixed number of days each year. So we could, for instance, fit some kind of a even non-parametric estimate, like a simple average. You can do it more fancy. You can use wavelets. You can use the Hodrick-Prescott filter, or a simple average. Let's say an average of the neighboring, I don't know, 1 week maybe, a rolling. So you take the average during the price during the week and you roll it along your series. And this is the result would be your red curve on this plot. We call it the long-term seasonal components because it kind of includes some kind of a long-term patterns which do not necessarily have to be of fixed period. The idea of this, what we had in this paper here originally, and then later used in different other papers, is you fit this red function to your data in the calibration window. You decompose it, meaning you subtract it from this gray line. You obtain this. So this is just your price after a log transformation, but in general doesn't have to be log. You subtract it. You fit your model, for instance, an ARX, to your data. Make a prediction for the next day, for the next 24 values here. Make a prediction of the red pattern for the next day. The question is how you do it. In the original paper, it was just we used the last 24 values and just kind of copied them. Add them back together, and this is your price forecast. And this works, surprisingly. I mean, this is a very simple technique. It helps improve. It helps to improve more on the simpler models. If you take more parameter models, more complex, it doesn't help that much. But still, it is a very simple technique that improves the fit. You can do a bit better with extrapolation. So here is an example from a recent paper from Journal of Commodity Markets, where here's the original idea where we took the last known part of the seasonal component, fitted using, I don't know, any technique I've mentioned before. And this is just copied to the next 24 hours to have a prediction of this seasonal component, to which we add the predictions of the stochastic component. Now, alternatively, we can think of it, we can do it this way, that first, forget about the red and the blue, just fit a model to your gray line, make a prediction for these days here, for the 24 hours of the next day, then fit your seasonal component, so the red and the blue one here to the extended series by the 24 hours, and use this part as your prediction of the seasonal component, and then subtract the red from the gray up to here. Make a prediction of your stochastic part. So let's say ARX. You add the blue one, and combine these two to get the price forecast. Okay. In this sense, you have the continuity. So there's of the seasonal component. There is no jump here. So in this sense, it also behaves better. And as we show in this paper, it improves the fit. So here's a plot with the results. If you have an E in front, like these two, so the purple and the red, those are with this extended seasonal component. The ones without are without it. The one here is a benchmark. Is just a simple ARX model, a small autoregressive model. The black curve, this solid black curve, is a Lear model, so it's a lasso estimate autoregressive model, which I will talk in a moment in detail. So it's a model which can have 100 or 200 original variables, which are selected by the procedure to be used later in the forecast. But when you compare the results, so compare the yellow and the purple is always below the yellow. So this procedure is better. When you compare the red and the blue, so the ARX type model without this extension, with the extension, again, the red almost always, except for a small period, is better than the blue, is lower, so the error is lower. So this technique improves and also improves. If you compare the purple with the black, the purple is better than the Lear model, which did not use this kind of a decomposition. So the composition also can help. Now, when we write our papers, we know all these things, but to be honest, we don't always apply all of them because we are studying some phenomenon, and this just complicates the procedure. But in theory, you could use all these different techniques I'm talking right now about, include in your model and improve the fit. They all should improve the fit on average. Okay. Idea number 3, combining forecasts. Already Arek today showed you some examples of combining probabilistic forecast. The idea of combining point forecast is super simple. Essentially, you have capital N individual forecasts. They can come from different models, from different experts. They can come from the same model, which is calibrated to different windows, anything you can think of. What you do, you take a weighted average of those forecasts for each moment in time. So you have, let's say, n models, so 1, 2, 3, and until n. You assign some weights, and this is your weighted forecast. This is your prediction. And this is usually better than any single forecast, or quite, I mean, maybe not in all cases, but in many cases it is better than any single forecast, except for very kind of correlated structure of these forecasts. If they are too similar, then this won't help much. But if there's some differences between them, this will help. Now, the question is how to select the weights. Okay. Well, if you don't know what to do, just take 1 over n. So Wi is equal to 1 over n. It works perfectly. The simple averaging really is a good, I mean, tough competitor. So to beat it, it's not that easy. I mean, you can do it, but it's, if you don't know what to do, just take 1 over n. Kind of like in portfolio analysis. And when you are trading stocks, you're building your stock portfolio. If you don't know how to do it, just take 1 over n in each stock. It's a very good portfolio. There are papers actually in the financial journals on this. The idea is really old. I mean, published at least in academic literature, at least in the 60s. And there are a number of authors that were discussing how to do it. Now, the names they use can be different. So you can, in the statistical econometric world, it would be, we would rather talk about combining forecast averaging, not model averaging, because not averaging models, we have averaging forecasts. In the AI engineering world, this would be more like committee machine, sample averaging, expert aggregation. So again, the same things, different names in different kind of subgroups or subdisciplines. So how to select the weights? Well, again, we have a whole zoo of different methods to select the weights. There's a whole literature on this. This paper here was 2015, so it's this one. Oh, it doesn't say here. Sorry, 2014, this one here. This paper is the first one. It's about combining point forecast to obtain point forecast. We test a number of methods. A bit extended version is in this article. So you can take simple averages, trimmed, Windsorized. You can have weights inverse to the errors of the particular models. This is one of the simplest ways you can improve. So you have, I don't know, 2 models, each has an error. Okay, E1, E2, you take the weights 1 over E1, 1 over E2, and rescale them so that they sum to 1. And that's it. So that's a very simple method. They can be regression-based estimate of the weights, eigenvector-based, many ideas, PCA-based, and so on. So there are many ideas, 3 papers where you can just have a look at different methods. If you don't know what to do, take the simple average, 1 over n. Okay. This idea, we had, well, I don't know, 2019, we published 2018 roughly, maybe 2017 we started working on it. I don't remember exactly, but just like always a question, what should be the training set that you use to train your data? And well, there's a similar question actually with the work with Tao we did a bit earlier on load forecasting with the sister models. It also has asked a similar question. So what information are we using to build our model? Here, the idea is very simple. We use exactly the same model, no changes between it. So for instance, the ARX model with roughly, I don't know, 10 maybe regressors. So it's auto-regression of order 7 at most. What I'm plotting here on the x-axis is the length of the calibration window. So starting from 28 days, this is the smallest, the first points here is 28 days, up to 728, so it's 2 years, 2 full years. We fit exactly the same model, but either to a very short window, and here's the forecast, or to a very long window, or anything in between. Okay? So the blue dots are the errors, the mean absolute errors of this model on some data. This is GEFCOM again, I think, for a particular window length. So like the optimal number, and you would probably never guess it, is something close to 62, if I remember right. Something here. So this is the optimal window length. You don't know it in advance. You know it exposed. Okay. So how to what to do about it? Well, you can take all windows and average everything. This is the yellow line here. This is this guy here, the yellow one. You take an average of the point forecast from each of the models, where model is the same, it's just the window has a different length. Okay, this is the yellow one. Well, we came up like a kind of heuristic where we take a few long-term windows, a few short-term windows, and this is much, much better, even much better, okay? So in the end, you have to take a few longer windows, like catch the longer-term trend, a few shorter to kind of adapt quicker to what is happening. So average over 4 or 6 windows, and this gives you really improvements on what is happening there. In the same paper, we looked at also at a neural net, so a nonlinear ARX model, and the behavior is the same. So, I mean, this average, all these averages, the kind of the symbols indicate what window exactly is taken for an average. So, like in this purple one, we are taking every month, I think, one. So every 28 days, there's a new model. But again, the few long ones, few short ones give you the best fit. So the lower the better, and this is the scale. So compared to the best individual model, you go from a level of roughly, I don't know, 6.95 to 6.6, let's say. Okay, so substantial increase, but by a very simple trick. And now you may ask, why here you have this kind of a smooth, narrow line, and here you have this fuzziness? Well, because this is a neural net, you get the randomness every time you estimate the model. And this is already, if I remember, an average over 5 runs of the neural net. So if I would just take one, this would go all over the place here. Could all go over the place. Okay, but this is a super simple technique. Okay, and one more. Okay, and we can do the same and looking at the simple average and the past performance weighted, where weights are 1 over epsilon. I don't know if 1 over epsilon here or 1 over epsilon squared. One of those. I'm gonna inverse. I probably want epsilon squared, so probably this one here. It is slightly better because this is this technique is this WAW kind of weighted average, and if you compare lines of the same color and compare a dashed line with a solid line, the dashed lines are slightly below. Okay, so it can improve slightly, but again, not on every data set, not in every case. So why bother? Just take the simple average. Okay, if you don't know to mess with. Now, we have seen here, this is one data set where you see, okay, the optimum was around here for a different type of model. So a neural network, the optimum was somewhere around here. So let's say, I don't know, 400 or 500 days. Here was 60 days. Here's a different data set. The optimum was somewhere between a year and a few months. How to guess beforehand? There's no way to do it, essentially. So averaging across the windows, over the windows used to calibrate, is a very powerful technique. And actually, when we wrote the paper, we realized that in macroeconometrics, there's a literature on structural breaks. We didn't think of it before, where you have a kind of a macroeconomic event, something really changing, like the presidential elections, and you have a change in the policy, and then everything changes. So you have models that have windows that go over this structural change, have shorter ones which are on the new period, and you average the results over those two. So that's a very, very simple, very powerful technique. Arek, if you can come and show the first snippet.
Okay, so now we will check out whether basically whether this averaging of across different calibration windows will also work on some more recent data. So as you remember, these papers were from 2019 and written probably a year before that.
Mm-hmm.
So we'll check it out on a more on some newer data sets. So first, as yesterday, we'll load the packages that are necessary, the data sets. We are still working on the Apex data set. So we start from 2022. We'll create lags for the ARX model. And after that, after we prepare our after we prepare our variables in array forms, we will create a list of windows which we would like to consider. So here we will start from 56 days and go up until 2 years every 4 weeks, not to spend too much time on the calculations. So we will iterate over the windows, and for each window in the list that we have established, that we have defined, we will estimate a model and assign it to a specified column in our data set. So here, this will be a column ARX, then the window size and forecast. After that, we will consider these two averaging schemes. So one of them will take into account all of the forecast from all windows that we consider, and the second one will only take the 3 shortest and 3 longest windows. So here you can see that for this particular thing, we'll average only 4 windows in the first 3 and last 3. So then we can plot our results. So let's start from the root mean squared error. And as you can see, so first thing, the minimum is in a different place than before. So before it was around 62. Now it's 476. So that would be difficult to guess. And you can see that averaging them performs much better than any of the individual models. And averaging only those 3 short and 3 long windows is actually even better than that, significantly better. And let's take a look how it looks like if we calculate mean absolute error. And here a situation is quite different. So now you can see that the minimum is in a different place. So now again, a very short window is actually the one for which we get the smallest mean absolute error. Again, averaging improves the forecast accuracy, although it is at par with the minimum. If we take the 3 shortest and 3 longest one, it's much better. So here you can see that if you are interested in minimizing both RMSE and MAE, the consistent way would be to just take the average of those. And that's all for this notebook.
Yeah. Thanks. Okay. And one more thing to see. I mean, as I mentioned, there's a complete different behavior here. So we are here these 3 short windows, 3 long windows. We are averaging something which seems rather good here, the 3 on this side, but 3 very bad. And still the average is really great compared to the rest. Okay? If you look at that RMSE, it's quite the opposite. Here is the pretty bad, and here you have pretty good. Again, the average is really great. Actually, we didn't start here the example from 28 because for 28 the RMSE was really high up. So it was really a bad model for RMSE in this period. I mean, this is a much more volatile period with much higher prices. This is the energy crisis, war in Ukraine. So it's way different from what was on the slides. Okay. Yeah. Other ideas for tips and tricks. Selecting training sets. Now you can. Well, here I was talking about selecting the window size, and essentially the windows were all ended today on the day you make the forecast and just started on a different period. But perhaps this is not the optimal way to do it. Perhaps we can take the last 2 years or last 4 years and select some subsets for training our models. And you can do it, as this paper shows, you can do it in a different space. And here the idea is that we take the price on 2 days, on the day we make the forecast, so we know the price. We take the load forecast for the next day, and the third dimension is the wind generation forecast for the next day. Okay? So you have this 3-dimensional object, and this red dot indicates where we are today. Okay? Now I can think of finding the most similar days in the past to today's conditions. And these are, well, for instance, using KNN, but you can use different clustering algorithms. And these blue dots are the ones that are the closest. Now, when we plot it in a kind of a time series fashion, well, we see that, okay, the blue ones are the ones that are really the high prices. So kind of, okay, it kind of is okay in the sense that the red dot, so today's value, is also one of the high prices. So we can just calibrate our model on all the data points, all the blue data points, and ignore the orange ones. Okay, this is the idea here. A similar one, but using something which is called change points or break points. Again, more in statistics, econometrics. Here you try to find periods of prices in this case, which are similar again to the red dot at the moment we make the forecast. So let's say the prices, first you identify when there are changes in your process. So these dashed blue lines, horizontal ones, sorry, vertical ones, were identified as changes in the regime of the process. And there are some different methods to identify it. And the gray ones were identified as something way different, so they are discarded, and the training is only on the black ones. Okay? So that's similar. One of such methods, originally published in this paper in JRSSB, is the narrowest over threshold. It kind of is a way to identify these breakpoints. So you have a data series of certain period, sorry, of a certain length, and you try to identify when the process changed its characteristics. And here you have two plots. The red line is the day that you make the forecast. So we start essentially, this is the first day we make the forecast. So on the first day, when we make the forecast for the next day, we use the window. The black indicates that we are using this window, the gray that we are not. So on the first day, we use the whole 2-year window. We do the same for the next few days, but then suddenly somewhere here changes, and we are not using a part of the data because it is too different of what is right now. Okay. And in this extreme case here, so for this more or less day when you make the prediction, you only use the really recent data, but a very short period before. Okay. This is for our 4 example, for our 18 from this paper. Again, you can compare it, and again from this paper the results are as follows: that the gray one, original gray here, this is just a simple ARX model fitted to every window. Okay, so this is like with the blue dots we had before. The dark gray are ones which are fitted to a model which uses area hyperbolic sine as a transformation first. So it's transformed prices. And you can see that essentially, for every window length, you have an improvement in this data set at least. This is not always the case. I mean, you can have an improvement. It can be large, like here, it can be small. On average, there is an improvement, but again, it's not always the case. So don't expect always. Then the averages, so the green dashed line, so this is the average of the gray ones. Again, it's better. And then some different versions of the averages. Essentially, in the end, this one here is an average of the 6 windows, 3 short ones, 3 long ones, after taking the transformation. And this is the green solid line. If you use selection of the windows using this method, this narrow threshold, you get slightly better, but not significantly. But as you can see here in the Diebold-Mariano test, there's no green cell here, meaning that this is not a significant. It's slightly better, but it's not significantly better. Okay, so each individual trick I've shown you generally improves the fit, improves the forecasts, not the fit, sorry, the forecasts. A combination typically also improves it, but it's not every case you try. So this is, again, trial and error. Some of these are really simple to implement, some are a bit more difficult to implement, but still much easier than any machine learning model. So still, you can try them. Okay, topic number 2. Let me just check the time. Okay. So first, I'll concentrate on essentially on shrinkage. This is the main idea here. And then a bit about deep neural nets, but I won't go into details about them. So if you have many, okay, in the ARX models, we are using just the price for the same hour yesterday, 2 days ago, and let's say 7 days ago, and that's it. But why only for the same hour? Why not use all prices of the day, of yesterday, of 2 days ago, of the last week, let's say even, and select only the ones that are really important. So in statistics, you have two simple ways to select your regressors in a regression. This is called stepwise regression. The one which is backward elimination. So you start from a full model. So you have, let's say in this example, just illustration, you have four regressors, and you check individual. If you remove, let's say, X1, and you on a test set you compare what is the fit. Then you add it back in, remove X2, see what is the fit. You do it for all four. You remove the worst one. So the worst one is removed. Okay. Now you have a model with 3 regressors. Okay. Then you do the same thing, repeat the same thing, and let's say X4 is removed from this spot, and you end up with 2 regressors. Now, based on what basis do you remove them? Well, you have some kind of a goodness of fit criterion. This can be, for instance, either the information criteria like archaic or Bayesian information criteria. This can be cross-validation. So essentially the goodness of it, how well, what I mean, the reduction in your prediction error on a validation set. Okay. Or you can start from you can do the forward selection, you can go the other way around. So start from an empty model, a null model, and then try which of the regressors improves the most. So is it just X1, is it X2, X3, X4? And let's say an example here, X3 gives you the most, if it's a single one. Then you select the next second best, let's say, regressor, and you add it to the model, and here you end up with these 2 regressors. Okay, so these are the 2 ideas for selection, but these are not really optimal. They can be used, they can improve over the simple model, but what is much better is shrinkage or regularization. I mean, they are not necessarily synonyms, but quite often they're used interchangeably. Now, the idea here is that we add some kind of a penalty. We add a penalty to the standard OLS estimator. So standard ordinal least squares is just this part. It's here the sum of squared errors. And you add some kind of a penalty. This penalty is, as you can see, is a function of the betas. So this is a function of your parameters, that the weights of your regressors. There's some tuning or regularization parameter involved, is lambda here. So this is like a single hyperparameter in the simplest models. You have to tune it somehow, or set it, or estimate it somehow. Again, cross-validation would be the option. 2 most popular methods are ridge regression and lasso, so least absolute shrinkage and selection operator. For ridge, you have a Q here is 2, so this is 2 for ridge. For lasso, it's 1. So those have kind of a linear sum of absolute values or sum of squared values of the betas. How do they work? On a very simple schematic drawing showing just a model with 2 parameters, so beta 1 and beta 2. Your parameter space, the one that you are minimizing, is essentially in L1. So in the sum of the absolute values is this one. So this is the shape of the beta 1 absolute value of beta 1 plus absolute value of beta 2. Whereas when you take squares, you get a circle. Now the contours of the least squares function, the kind of ellipses, and the fit is where they touch this blue object. So in the ridge regression, if you can kind of have 2 circles, it's quite likely they will not touch on the kind of axis, but somewhere else. Whereas if this is the kind of a tipping points here, it's quite likely that this will touch exactly on this point. Meaning that if it touches here, you eliminate beta 1. It's out of the model. It has a value of 0. So you're only left with beta 2 in your model. Okay. So this is the big difference between the two. So ridge will shrink the coefficients because there's a penalty. So it will penalize the very high values of betas, whereas lasso will shrink some of them to 0, meaning eliminate from the model. Well, essentially I've said this. So in ridge regression, you have the sum of the beta squared. As lambda increases to infinity, then beta tends to, so if you increase lambda, the betas all shrink to 0, but that's not what you want to do. So lambda has to be something smaller. But as long as lambda is not infinity, the betas remain non-zero. So meaning all predictors stay in your model, just have much smaller weights. With lasso, when you have the penalty is linear, then if lambda is larger or equal to 1, all betas are zeroed. There's no beta in the model, so it has at most 1. So as lambda approaches from below 1, more betas become 0. And the final model doesn't include all predictors. We can visualize it here. So we have in the 3 models. Okay, there's something in between. So the ridge regression was just this term, lasso is just this term, and elastic net introduced in 2015. It has both terms essentially. Well, the cost is another parameter, another hyperparameter. So here we had lambda before. Now we have also alpha. Okay? Extra parameter has to be calibrated somehow. But this is something in between, so it's kind of a blown up square. The edges are a bit bulky here, but still not a circle like here. So this is something in between, and in fact, this model, the middle one, will in general will be better than both the lasso and the ridge, but at the cost of an extra parameter. Now, if you look at the betas, so this is increasing lambdas in this direction. With ridge regression, the parameters, well, they are shrunk, okay, but they're not 0. With lasso, at some moment, this is the moment when this parameter just became 0, this beta became 0. Here, this yellow one, and here, after this, all of them are 0. Well, elastic net is something in between, kind of betas are slightly longer staying non-zero, but the effect is very similar. So what about performance? Okay, here's a comparison from our earlier paper where you take, okay, the naive, forget the naive, take the ARX. This is the model we have been essentially working on before. So lax 1 to 7, 3 dummies for Monday, Saturday, and Sunday. Also a daily minimum which is added to the model, and a load forecast. And for comparison, we take the large model where you have over 100 variables, and this includes all prices for the for the 3 days plus many more variables. So almost 100 variables in total. Now comparing these two, well, it's not always the case that the bigger model is better. Okay, you have many more parameters to fit. It doesn't mean it's going to be a better model. But if you use selection or shrinkage methods, so you start from this model with 107 parameters, but then use one of these techniques here, you generally get better. So the forward selection and backward, these two here. So, oops, just lost connection to the pen, but don't worry. So if you have these two guys here, they are not really great. I mean, they work, but not so well. Ridge is also not perfect. But then lasso and elastic net, they are the greenest ones here in all cases. So, and lasso, okay, slightly worse than the elastic net, but it has one less parameter. So perhaps for parsimony, we choose lasso. And this is what actually we choose in most of our papers. If you want to get extra few, I mean, whatever percentage point, or not really percentage points, much smaller value change improvement, then you can maybe try elastic net. But again, one more parameter to fit. Lasso has this also interesting feature that you can analyze what kind of variables have been selected in the models. So here in this model, which includes all prices for the previous days, 2 days ago, 3 days ago, 7 days ago, we have load forecast for the 24 hours, wind generation forecast for the 24 hours, and so on. You can measure how often in the calibration window a given variable was selected. The greener the color, let me maybe increase this. The greener the color, the more likely the parameter was selected. So if it's very green, these parameters like these ones here were almost always selected. So for predicting today's price, let's say if we want to go hour 18, so 6 p.m., the most important values are yesterday's load forecast for today, for midnight, for the last hour of the day, not for hour 6 p.m. Well, this is hour 6 p.m. It's also important. And also the morning peak. Okay? So this technique, which selects automatically the regressors, also gives you information of what variables are important, and you can use it to build your own parsimonious simple models, expert models. And some of these, when we first saw such graphs, we first plotted them, we're kind of surprised how often the end of the day is important for all the hours. So this is kind of the last. I mean, we didn't think of it before. Maybe some of you knew it before, working with the data, but this was a surprise for us. So this gives you some information which perhaps you may not know. What is important and what is not. Yeah, so of course the diagonal means that it's the same hour that you are forecasting, but the morning peak and the last hours of the day, they are really important for making the predictions. Okay, Ari, can you show the second one, and then we stop the first part?
Okay, so now we'll take a quick look at the comparison of retrogression and lasso. Let me check. Yes. Did it run? Okay, great. Okay, so as before, we load the packages that are necessary. We select the data set. Again, we'll use EPEX. We create lag columns for prices. Now the first main difference is that we will define our own class called regression, and this will allow us to solve a regression problem with regularization, with shrinkage. So there are three parameters, actually, three fields that our objects will have. So or the arguments, like we'll have the number of inputs, the regularization parameter, and for regularization parameter for L1 and regularization parameter for L2. So L1 is lasso and L2 is for ridge. So we assign the fields of our object. So the weights will initialize them to be 1 divided by the number of regressors, the bias, and we put the penalty that we provided as an argument. Now for the prediction, we will just multiply the inputs by the weights and add the bias. And now the core is the calculation of loss functions. So the loss function will be constructed from the mean from the mean of the squared errors, and lasso penalty and ridge penalty. So here lasso penalty is just the sum of absolute weights in our model, and the ridge one is the sum of squared weights of the model. And then we add those three terms together. So in general, this class allows to use elastic net, basically, but we will here compare just three models. So one will be without any regularization, one will be with lasso, and one with ridge. Okay, so now we define our calibration window for the forecasting models, prepare the inputs and outputs, assign some model names, and create two periods, one for training, one for testing. So the one of the differences between this notebook and the one that we did previously is that we will not use rolling calibration right now. We will just train our model, train our models once on the training set, and then check how they perform on the test set to save some time and make the analysis of the weights of the models easier. So now we'll iterate over hours. And another difference is that before we used just 4 explanatory variables in our autoregressive model. Now we'll use 96 because we will use we'll use data from all the previous hours, from all the lags up until 7 as well. So in this setup, we will have to add the regressors from different hours to our pool of regressors. The second important thing is that because we use penalties, we want to scale our input so that they are on the same scale, basically. So we will subtract the mean and divide by standard deviation of each input, like separately. That's important because if we have data that has differently scaled inputs, obviously the penalties will affect the weights that correspond to the inputs that are, well, small, and then they need high values of the weights. So now, after preparing the test data, after scaling it, we fit the models to our scaled train data. So that is denoted by XZ and YZ, the scaled ones. Then we run the predictions, and we do and we transform back our prices that we also, our response, which we also scaled, but only using a z-score. So we only subtracted the mean and divided by standard deviation. And now we can plot the error metrics on this on those three different models. Maybe one thing that I also note here. So here, when we create a regression model for each model in the set that we constructed, we call a dictionary called params, and you can see that this dictionary here a little bit above defines the arguments for the constructor of our regression class. So here for lasso, we will just take the L1 penalty to be equal to 0.1, and for ridge, we will take a value of 1 for the L2 penalty. These were just selected to get some results that present some qualitative differences that we expect. So now let's take a look at the results on the training period. So you can see that the autoregressive model without any regularization actually gave us the smallest root mean squared error on the training data set. And this is actually to be expected because we expect that it can overfit our in our data set. So now when we take a look at the testing period, what happens is that it really is the case. And the lasso, the regularized versions, the one with lasso and ridge, although they perform worse on the training period, so they have a worse fit in general, they generalize much better and perform much stronger on the testing. So in the end, we would like to show you how the weights of this model behave under these regularizations. So as you remember, like for L1, for lasso, we expect that it will shrink most of the variables, or at least some of the variables, to 0. And for a ridge, this is probably not the case. It will keep the weights small, but not cut those regressors out. So let's take one of the hours just to take the model corresponding to this particular hour, and let's sort the absolute values of weights. And then let's plot them on a single plot, and let's see how they look like. So as you can see, actually the ARX model has really a large magnitudes of weights, and we can't really see that much for the lasso and ridge one from this plot. But you can see that the green line, like the green area that corresponds to the weights of the ridge model, ridge regression, doesn't really shrink to 0. It's always visible. Maybe let's change. Oh, so this, I'll have to run it again then. Okay. Okay, so I'll not run it again now because it will take some time. Okay, so the thing that we, can I maybe somehow zoom it in? No, not really. Okay, I don't know how much you can see from there, but the thing is that the lasso allows us to have some large weights despite the fact that we have the penalty. Yeah, but probably doesn't. But it will anyway. We'll have to run the.
I know.
again.
No, we'll run it. It's not a problem. But
Okay,
let's
let's
run all,
Yeah.
and you'll see that this actually notebooks they run. If you haven't done it yourself, they actually do. But dude, we need a few minutes.
Hopefully.
Hopefully.
Yeah. So you can see from there that the orange one is above the green one. So this means that we allows us to have some high weights compared to ridge. And when the notebook will actually will run and will set the limits to be a little bit smaller on the Y scale, then we'll be able to see that ridge will keep almost all, if not all, of the regressors in the model, while lasso
still running. Okay.
Yeah, it is running. Yeah. So you can show it in a
okay,
second.
well, in a second. When it runs, when it's complete, I'll show it again. So it's okay. It needs, I don't know. I don't remember how much this we need.
Take around a minute or two.
Minute or two. Okay, so let's go back to it. So before we go, well, let's go back quickly here. I wanted to okay, one more comment in this context. Lasso, ridge, and elastic net are just three different methods, but there's many more. And actually, if you want to look how other perform, this is a recent paper by Bartek Oniewski, my former PhD student, where he tested 10 different penalties. And only, I mean, the best were the elastic net and LQ, where the power here is a number between 1 and 2. Okay? So these two are best. Lasso was just trailing behind. So if you want to do it optimally, you can do it, but the problem is both elastic net have two hyperparameters, and also LQ this is the Q and this is the lambda. Okay, so the question is whether you have slightly better model, more hyperparameters to decide on or train, or you want to do it. But okay, you have here is a recent study on that shows you how this works. Let's see if we have the results by now. Yep. Okay, 1 minute 14, not that bad. And yeah, okay, so here now we just limit the access, and you can see that the weights of ridge, the green ones, they are all non-zero, whereas lasso, well, only the top, I don't know, 10, 15 weights are still in the model. The rest is canceled out. Now, when RX said that we have all hours of the week, we don't have it, but because then we would have at least 168 regressors. We have 96 because we have day before, 2 days before, 7 days, that's 3, plus the load forecast. So it's 4 times 24, 96 regressors. That's where it comes from. So yeah, that's what it is. And well, we've given proof that actually the notebooks work. Okay. So lasso, I mean, it's not a very difficult technique. Some people already say this is already machine learning. Well, this is very simple machine learning, but still it is. You have some kind of automatization of what is done here. And a very quick comment on deep neural nets. I mean, we will need a whole new workshop to discuss and tell you everything about the neural net. So I'm not going to do it today, definitely not. The takeaway, I think, would be that the biggest, I mean, in my opinion, the biggest advantage of using neural nets is that you can have multiple outputs. Okay, you can have a neural net which has single output. You can have a complex one. Maybe it'll be slightly better than a regression or lasso estimated regression model. But the biggest advantage is that you can estimate all outputs, or let's say all hours of the next day at the same time. So 24 outputs. Building such a model in a kind of linear regression setting, you end up with vector autoregression models, and they have too many restrictions to be really useful. So we've never been able to really get good results with vector autoregressive models, whereas we can get good results with neural nets which have multiple outputs. So this is, I think, the biggest advantage. I mean, running a model, such a big model with one output is only, I mean, maybe 2-3 times faster than running it with 24 outputs. So this is much more efficient to already have the full vector that you want. And in a way, this approach preserves some kind of a dependence structure between the prices of the neighboring hours, which is also important. So that's something that is to be considered. Now, what about performance? Now, here's in this paper that already we've heard in the previous talk on the price forecasting competition. This paper introduces the Lear model and the DNN model. The Lear is the lasso estimated model around 100 regressors, but estimated by lasso. So we end up with a dozen or maybe two at most. The DNN is like a network like this one with already a multiple output network. This is a DNN that we have there without this. So it's only feed forward, so there are no connections that go back. So it's a relatively simple structure. Here we report in kind of a fancy fashion relative to a naive model. So if it is something like 0.6, meaning this is we are 60% of the naive errors for this data set. And as you can see, the green patch is inside the gray one, meaning that the errors are slightly smaller. There's a bigger difference for the German market, whereas here for the French, there's a small difference, but still there is some difference. Okay, so the DNN model, so the neural net, is slightly better, probably even statistically better. We show, I'm not sure, probably for not all data sets, the results were statistically significant, like using a Diebold-Mayer anti-test. But the costs are huge. I mean, training the calibration of the hyperparameters can take a few weeks even. I don't know how if you have recalibrated or you have just used the codes there. Well, then you have a fast machine, or maybe he used a simplified version which is available on the web page. Whereas in the paper we did a kind of more thorough study. It took us weeks to get the hyperparameters right. So this is something you cannot do every day. And also in the paper that Arek was mentioning, and I will also some comment in the next hour, hyperparameters we usually do it once, so they may have kind of a fixed window for the hyperparameters and then just train the weights every day. Okay? Kind of a compromise between time and accuracy. So you can get a bit slightly better. If you want to play around, here are the Python codes for the models. Another comment. So as I said, for the DNN, there's a simplified hyperparameter search routine in this implementation. So if you want to really have it done thoroughly, just have to look at the comments in the code. The Lear also used here as a bit faster algorithm. You can do it better. You can do much better actually. So if you are interested in using these models, contact me or anyone from my group, and we can give you advice how to make these models run even better than what's in this toolbox. Now, the last slide from this section and this part of the talk is about interpretability. Okay, well, there's many things have been said about interpretability of machine learning methods. Generally, there's close to none. Some models have limited interpretability. Now, when we publish this paper, we marketed this as an interpretable AI. Okay, it's a bit of an overstatement, I admit it. It's only partially interpretable. What is this partial interpretability? Okay, we are able to identify in this structure which kind of is based on the n-bit structure. So we kind of extended it to include exogenous variables. But essentially, you're able to identify parts of your network which are responsible for representing parts of the signal. So you are decomposing the signal into trend, seasonality, exogenous factors. So you can have many of them, of course. For simplicity, we just list three here. So you have parts of the network which represent this, and but then what is happening inside of each stack and inside each block? Okay, that's again a black box, really. So it's not a full interpretability. We understand partially what is happening. The results, if you want to experiment yourself, these are the codes here. You can play around with them. They are more computationally intensive than the DNN model. The question is whether they are any better. Okay, this is a comparison from this paper. And this is this interpretable version from the paper. The DNN model, there was some error in the original paper actually in this one. In this paper there was some errors. We wanted to publish an errata, but then the publisher said no, so It's online available. There's a link here, but these are the results for the corrected results. So there was a minor issue there. But anyway, looking at these results, for some markets that we looked at, the DNN was better. For some market, it was the NBITS was better. Looking at the time comparison, the DNN 50 seconds for daily recalibration on some machine, 80 seconds, so like what 60% longer for this one. And guess what? Hyperparameter optimization much longer, of course. The question is it worth it? If you are just after more accurate forecasts, I wouldn't go for it. It's just too time consuming. You could probably even actually stick with this model, which is much simpler. And as you have seen in the competition, it beats the best performers, right? Okay. Okay, that's the end of this part of the first part. Any questions? Yeah.
I have one question. So the recalibration, trying different recalibration windows for the ARX model, that's like having different training data sets and then combining the model together. Have you tried the same approach but for any other model, not ARX, but let's say DNN or something? I know it's expensive to do, but
well, in this plot you have ARX and a neural network. And ARX, the one here, this is the neural net. So this already is. I just lost my pen. Okay, I'll have to look for it in a moment. Yeah. So the one on the left here, this is the neural net. So it's a neural net with the same inputs as the ARX. So the simple neural net with, I don't know, 10 roughly inputs and one layer only, one hidden layer only. But okay, it works again. We have lasso estimated models. One of the recent papers, if I believe it. On Windows. So lasso estimated models, yes. So large regressions on lasso estimated models. The DNNs, have we tried them or not? Don't think so.
DNNs actually use years of data. So the large model, they are very small. So you can use structured calibration, but for some neural nets, if you have a really large number of parameters, then you just have to use longer windows.
I would be curious to try it on the rebase model. They are also interesting.
Yeah, but the biggest benefit, I mean, in this case, in the simpler models, is really short windows and really long ones. Whereas, so if you need a lot of data to calibrate the model, you can't have the short windows anyway, so you won't catch the short-term fluctuations. So, yeah.
Any other questions?
Hey, so forgive me if this is a preliminary question here, but say you're forecasting tomorrow's price. What is the training data in these different windows? Are we talking about taking more lags, or are we just talking about different training sets? When are these training sets?
Okay, 728 means we take the last 2 years of data of all the regressors that we have in our model. So let's say it was a day before, 2 days before, 7 days before. Okay, and the load forecast, let's say. And we take matrix of all those regressors for the last 2 years. Okay, so this is the 728. The shortest one here is 28. So you take, again, the same regressors. And in rows, you have only 28 rows representing 28 days. Okay. So this is the number of data points on which you train your model. Right? The regressors are just, they don't look back 2 years ago. No, the regressors just look a day, 2 days, 7 days at most. Yeah, something like this.
Any other questions? Yeah, just at one point, when you're going to the lasso approach for the AR approach, an hour 18, you notice that hour 24, the day before was really significant for the load forecast. I wondered if in the Spanish markets, when they decide their unit commitments for the next day, that happens roughly like 20 a.m. or whatever. Therefore, the last floor.
No, but these these are known already in the morning, so it's okay in this. Let me check. No, this direction. Sorry. Yeah. This plot. So in the yesterday's load forecast for today. Okay. So the load forecast is made in the morning. And it's made. Okay. So if it's made yesterday, so it's okay. It was made yesterday morning load forecast for today, and that's it. It's kind of it's not nothing related to unit commitment there.
Well, just might relate to the setup and how they choose how the data may go. I don't know. It's an interesting way.
It's kind of like a part is looking forward information. I mean, the most looking into the future about the information. I mean, the most forward-looking information in the future that you have. So hour 24. And somehow the end of the day catches the variability of also the hours before midnight. Yeah, I mean, it's not obvious why this is the case, but this is the case in most markets we have looked at, with different intensity, of course. But yes, this I don't remember which one is taken from, but okay, if you look into our papers, you'll see exactly on different markets how this looks.